Hello everyone, this is Group 6. Today we are going to talk about our CS7200 machine learning project, whose title, which is shown on our refreshing poster, is SVM on Imbalanced Dataset and Kernel Hyperparameter tuning through PSO. The dataset we analyzed in this project is a highly imbalanced dataset about the credit card transactions, where most of the cases are normal cases, but only a couple of hundred cases are fraudulent transactions. Usually, imbalanced dataset will skew training algorithm. Support vector machine, however, is an algorithm that still does a good job in classifying both classes in those highly imbalanced datasets. Our first step is to balance our dataset. The approach we took on this project was called downsampling, which means we randomly sampled data observations from the major case so that both classes can be balanced. After the balanced dataset is obtained, we need to use SVM to train and test the dataset. The key part, which is also the hardest part of SVM, is the choice of kernel function and the hyperparameter with kernel function chosen here. An approach we search for hyperparameter method is PSO.
Now let's shift our focus towards the hyperparameter tuning process. PSO, which stands for the particle swarm optimization, is the algorithm that we have implemented in the kernel hyperparameter tuning process in support vector machine. As the name suggests, this algorithm allows one to have more than one search members or particles in a search team that is looking for an optimal solution on the objective function surfaces. Each randomly moving particle's new position is influenced by its best achieved position, which is also called its personal best, and the group's best position, which is also called the global best. If we look at the figure 4 here, the red circle is the position at iteration 0, the green circle is the personal best, the blue circle is the global best, and the particle's new position is determined as the sum of personal best, global best, and its own velocity. The new position is shown by the black circle. We implemented PSO for the in-class scatter, between-class scatter, and accuracy as our objective functions. It is intuitive to minimize the in-class scatter because we want the points in different classes to be clustered closely to each other. On the other hand, it makes sense to maximize the between-class scatter because we want the distinct classes to be as far away from each other. The figure 3 attached here and the equations for in-class scatter and between-class scatter can help understand this better. This optimization would lead to a better linear separation in the feature space, as shown in the figure here in the left bottom corner. This motivated our first research question. That is, we wanted to understand whether this PSO algorithm would search for better accuracy for the SVM model we fitted to our datasets. We compared its performance with the sklearn library search methods like exhaustive grid search and random parameter optimization. And turns out our results matched our expectation very well. The PSO helped us achieve from 3.5 to 16.67% increase in the accuracy in comparison to other state-of-art methods. For example, in Gaussian generated imbalanced dataset, PSO achieved 71% accuracy, whereas the exhaustive grid search and random parameter optimization achieved only 62%. Or another example, in Gaussian generated balanced dataset, The PSO achieved 63% accuracy, while the exhaustive grid search and random parameter optimization achieved only 54% and 55% respectively. So this was about PSO, and now Yang Lei would continue with the second research question.
For the second question, we want to answer which kernel functions achieves better performance in SVM model. We try different parameter setting and different methods. From that, we conclude that across both the variants of datasets, polynomial kernel hyperparameters have achieved 5 to 10% higher accuracy than RBF kernel hyperparameters using EGS and RPO methods. Using PSO algorithm, polynomial kernel hyperparameters has achieved 0 to 5% higher accuracy than RBF kernel hyperparameters. How does this imbalanced dataset affect hyperparameter tuning process in SVM model? This is the third question, and it's turned to Youzhi.
For question 3, the PSO algorithm achieved 0.4% lower in class scatter on imbalanced version than on the balanced version. It also achieved 13 to almost 6,000 times higher between class scatter on imbalanced version than on the balanced version. This suggests that it's easier to linearly separate the imbalanced version in feature space than the balanced version.
Okay, thank you, Youzhi. And the last research question that our project tries to answer is if there is a need to consider alternative objective functions in the tuning process of support vector machine kernel hyperparameters. And why is this important? This is important because as accuracy requires us to fit the support vector machine model, it is expensive to evaluate in comparison to other objective functions like in-class scatter or between-class scatter objective functions. And from the experiment performed in this research by me and my teammates, we noticed that the hyperparameter value for the RBF kernel that corresponds to the minimized in-class scatter objective function is the same as the one that achieves maximum accuracy by the extensive grid search method. Also, the hyperparameter values for the polynomial kernel that corresponds to the minimized in-class scatter objective function is the same as the one that achieves maximum accuracy by the random parameter optimization method. This indicates that maximum accuracy of the model is gotten by minimizing the in-class scatter objective function. With this and the other research question talked about by my teammates, our group would like to conclude by strongly suggesting the implementation of particle swarm optimization algorithm in the hyperparameter tuning process of support vector machines. Additionally, there is strong indication towards using the in-class scatter objective function as an alternative objective function in the tuning process. And that's it from Group 6. Thank you for your time.